This video shows different examples of solving for the derivative of transcendental functions. Check how they proceed here in differential calculus. The first example is for the derivative of arctangent of 1/2 x. Having an inverse trigonometric function, the derivative of arctangent is the prime of the angle all over 1 plus the angle's square. In this case, the angle is taken as half of x. So, if we take this as u, we can solve for u prime as 1/2 times the derivative of x with respect to x, which is taken as 1. So u prime is simply 1/2. U squared, on the other hand, is the square of 1/2 x, which is x squared upon 4. Substitute them in the y prime equation and simplify by taking the LCD in the denominator, that is 4. Proceed with the operation to have half of 4 all over the quantity of 4 plus the square of x, which can be reduced as the final y prime, which is equal to 2 all over the quantity of 4 plus x squared. The second example requires the derivative of ln of the quantity 1 plus e raised to negative x. The derivative of ln u is equal to u prime upon u. In the problem, u is ln of the quantity 1 plus e raised to negative x, and u prime is taken by another ln operation. This time, we name the simple term as w. Take the derivative of w as the derivative of 1 plus the derivative of e raised to negative x. Again, the second term takes the derivative of an exponential function, which is in the form e raised to its exponent r times the derivative of the exponent r. So the derivative of w, or we call w prime, is 0 plus e raised to negative x times the derivative of negative x, which is taken as negative 1. Thus, w prime is negative e raised to negative x. So if we go back to the derivative of u, which is w prime over w, and that is negative e raised to negative x over 1 plus e raised to negative x. Knowing u and u prime completely, we can take y prime as the ratio of the fraction negative e raised to negative x over the quantity 1 plus e raised to negative x, and ln of the quantity 1 plus e raised to negative x. We simplify the equation into a single fraction bar, and that makes y prime as negative e raised to negative x over the quantity 1 plus e raised to negative x times ln of the same quantity 1 plus e raised to negative x. Next is the derivative of ln of 1 plus e raised to negative 2x over 1 minus e raised to negative 2x. With ln, its derivative is again u prime over u. So the whole fraction is taken as u, then we look for u prime. Having a ratio, we have to use quotient rule, which can make the equation truly long. That is, take the denominator as the square of the original denominator and use low d high minus high d low. The next challenge is to take the derivative of the natural number e with its exponent and that is through the pattern e raised to r times dr all over dx. In the problem, we take the derivative of e raised to negative 2x as e raised to negative 2x times the derivative of negative 2x with respect to dx, and that is simplified as negative 2 times e raised to negative 2x. If we get back to u prime, we can shorten the equation by taking out the derivative of the constants. Then plug the previously solved negative 2 times e raised to negative 2x as the derivative of the second term. Simplify the signs to shorten the equation, and factor out negative 2 e raised to negative 2x. We can simplify the terms left in the bracket, and that is by cancelling out negative and positive e raised to negative 2x. So we are left with twice of negative 2 times e raised to negative 2x all over the square of the quantity 1 minus e raised to negative 2x. This can be simplified further as negative 4 times e raised to negative 2x all over the square of 1 minus e raised to negative 2x. Now getting back to the derivative of y, we place the two terms u and u prime. Notice that we can cancel some denominators, leaving the equation as negative 4 times e raised to negative 2x all over the quantity 1 minus e raised to negative x times the quantity of 1 plus e raised to negative 2x. Note that the binomials in the denominator form the difference of two squares, so we can reduce them as the square of the first term minus the square of the second term. If we simplify it a little more, we get negative 4 times e raised to negative 2x all over 1 minus e raised to negative 4x. Example 4 has y equal to the root of 1 plus cosine theta all over 1 minus cosine of theta. Recall from your trigonometric identities, particularly half angles. One identity has the tangent of half angle theta is the root of 1 minus cosine theta over 1 plus cosine theta. Since we have plus over minus in the problem, we can flip the numerator and denominator and have the reciprocal of tangent of theta over 2. We use this in taking the derivative of y, and that is the same as the derivative of tangent of theta over 2 raised to negative 1. So by power rule, we can take the exponent, negative 1, times the term tangent of theta all over 2, this time with the exponent of negative 2, times the derivative of tangent of half of theta. Again, the derivative of tangent u is the square of secant u times du all over dx. So the derivative of tangent of theta over 2 is secant squared of theta all over 2 times the derivative of theta all over 2. This can be simplified as 1/2, so the resulting derivative is half of secant squared of theta all over 2. So the final y prime is solved as negative 1 times tangent of theta all over 2 raised to negative 2 times half of secant squared of theta all over 2. We can use more identities to shorten our answer. So we convert secant squared as the reciprocal of cosine squared theta all over 2. And also tangent squared theta all over 2 can be expanded as sine squared all over cosine squared of theta all over 2. Plug these identities in the original y prime equation and cancel out similar denominators to have y prime as negative 1 all over 2 sine squared theta all over 2. To take the denominator out, we can write y prime as negative half of cosecant squared of theta all over 2.